Now I'd like to introduce you to the Maxbotics MB1010 Sonic Rangefinder. We'll look at features and pinout, sonar ranging principles, temperature compensation, and beam characteristics of this device. This rangefinder is included in the NI Myrio Mechatronics kit. It's the Maxbotics MB1010, also known as the LV Max Sonar EZ1. This particular unit has a customized pinout compatible with Digilent PMOD boards. Let's review some of its features. It has range measurement from 6 inches out to 254 inches, or 15 centimeters out to 6.5 meters. Objects closer than 6 inches range as 6 inches. It has a maximum 20 Hz update rate with 3 output styles: UART at 9600 baud, analog output ranging from 0 to VCC, and pulse width output at 147 microseconds per inch. You have free run and triggered modes. The supply voltage can be 2.5 to 5 volts, and this device optimizes sensitivity and narrow beam width. Applications for sonic rangefinders include distance measurement. This would be a non-contact sonar ranging technique, object detection and proximity sensors, and robotic world mapping. Let's take a look at the pinout and signals associated with this board. 6 pins altogether. You have pin 1, 2, 3, 4, etc. up to pin 6. Pin 1 is the analog output, abbreviated as AN. You can determine the measured range in inches by taking this analog output voltage, dividing by your value of VCC, and multiplying it by 512. This assumes that the temperature is room temperature, 22.5 degrees. Pin 2 is the ranging mode, RX. High level means free run, and you get a new measurement every 50 milliseconds. Pull RX low to stop ranging. Now you have an internal pull-up resistor keeping RX pulled high. You can instead set RX low and then pulse it high for at least 20 microseconds to take a single measurement. Pin 3 is the UART transmitter, 9600 baud, 8-bit, no parity, and 1 stop bit. You get 5 characters for each measurement, beginning with R, followed by 3 characters for the numerical value of the range, and then followed by a carriage return. Because this measurement is an integer, you have 1-inch resolution. The carriage return in hexadecimal is 0D. Pin 4, PW, or pulse width output. You need to measure the time of the pulse width, it's a high level, and then divide that by 147 microseconds per inch to determine the range. In a similar fashion, this measurement also assumes that the temperature is at room temperature. Pin 5 is the ground, and pin 6 is the DC supply. You can use the Myrio 3.3 volt supply or the 5 volt supply. Now let's take a look at the principle of operation of the sonic rangefinder. The black cylindrical structure is the transducer, and you can think of the transducer as being a combination of a speaker and microphone in the same device. The measurement process begins by applying a short tone burst to the transducer. The transducer is operating as a speaker at this point and launches a traveling wave pulse. This tone burst is 13 cycles at 42 kilohertz, just outside of the range of human hearing, which ends at around 20 kilohertz. The wavelength, abbreviated lambda, is the speed divided by the frequency. Speed is abbreviated nu, and in room temperature is 345 meters per second. This gives us just over 8 millimeters per cycle. We have 13 cycles altogether, and that means that this traveling wave pulse is about 11 centimeters or 4 inches. Now it's propagating at 345 meters per second. It bounces off the target. You can think of that as an echo. And now the transducer is acting like a microphone. This received sonic pulse is translated back into electrical form. Now, a certain amount of time elapsed sending the pulse out to the target. that same time is required for the echo to return back to the transducer. Now, we are interested in determining the range, that is, the distance from the transducer out to the target. Because we know that the combination of the send time and the return time, also known as time of flight, because we know that we can measure that quantity, from that we can determine the range. So we do so by looking at our value for speed. This is, again, 345 meters per second in room temperature. Multiply that by the time of flight. That means we have meters per second times seconds, and the seconds is canceling out. Now, because the time of flight is actually 2 trips, we need to divide time of flight by 2 in order to determine the time that we need out to the target. So we take 345 divided by 2, multiply it by the time of flight, and then we get the range in meters. Again, this is based on the time of flight being measured in seconds. Now, the PW output provides direct access to this measurement process. PW goes high when the pulse is first launched from the transducer. It remains high until the return pulse is detected. This time of flight information is directly encoded into this pulse style waveform and serves as your primary measurement. Now, the range calculation in this case can be summarized as time of flight divided by 147 microseconds per inch, and that gives you range in inches. I'd like to mention that because this pulse is on the order of 4 inches long, this sets a lower limit on your ability to range a target. For the MB1010, this lower limit is defined as 6 inches, and anything closer than that will simply range as 6 inches. The MB1010 requires at least 14 inches of clearance to perform a proper self-calibration. You'll need to power cycle the rangefinder to recalibrate if you have any significant changes in air temperature, humidity, or supply voltage. Now, if you have access to an independent measurement of temperature, you can perform your own temperature compensation of the range measurement. Turns out that the speed of sound varies fairly dramatically with temperature. Here's the specific equation. For example, let's look at the variation in the speed of sound over the rated temperature range of the MB1010, minus 40 degrees up to plus 65 degrees. You can see that the speed of sound increases with temperature from 306 up to 369 meters per second, and that's a 21% increase. Now let's finish up by looking at how Maxbotics describes the beam characteristics for their transducers. Here I have the transducer in a coordinate system. I'm looking at it from the side view. This is the range direction, call that R, and then the side-to-side direction here is X. This would be the distance from that center line along the range. Each square on the graph paper here is 30 by 30 centimeters, or about 1 foot on a side. Now this closed contour indicates the detectability of a 3¼ inch dowel rod. The rod can be detected provided that it is inside this contour. This particular contour is for a supply voltage of 5 volts, and this contour is for 3.3 volts. So you'll notice that with a lower voltage, your ability to range objects is reduced. Now, a similar measurement taken for a 1-inch dowel rod. Note that in this case, the range ability is reduced. You can think of it as you can't really see this smaller object unless you are closer to the transducer. Please refer to the datasheet for additional beam patterns for the MB1010 as well as the other Maxbotics devices.